Thank you, Jill, and the organizing committee and the E3SM leadership team for this opportunity to present you the EAGLES project progress in the last 2.5 years. My name is Po-Lun Ma. I'm the PI of the EAGLES project. This project, just give an overview of this project. This project was funded in late 2019, and the project aims to develop improved treatments for aerosols and aerosol-cloud interactions for the global convection-permitting E3SM version 4. To achieve that goal, we developed 3 model development themes. Theme 1 focuses on aerosol processes, and Theme 2 focuses on clouds and aerosol-cloud interactions. And Theme 3 focuses on computational efficiency and trustworthiness. We also established this cross-cutting activity to establish 4 different liquid cloud testbeds, if you see on the right here. And per the request from the original FOA, we focus only on liquid clouds in this phase. But even only for just liquid phase clouds, there are different kinds of liquid phase clouds. So we need to cover a wide range of liquid cloud regimes. That so we selected these 4 different locale. One is the Eastern North Atlantic, and then the Central US. Then here is the Northeast Pacific, and then Southern Ocean. And these 3 regions covers from marine stratocumulus to shallow cumulus, and also the shallow cumulus and the other types of shallow clouds in the over the continent. In the Southern Ocean, you can see that there's no signals from aerosol-induced cloud radiative forcing. So this area is typically considered as the proxy for PI, pre-industrial conditions. So that's why we also picked this locale. This is a large effort that requires a lot of collaboration, and we combine expertise from 2 national labs and 5 universities to achieve that goal. So the primary work that we are doing here is that we are trying to improve the treatments for sea spray aerosols, mineral dust, wildfire aerosols, biogenic SOA, and anthropogenic carbonaceous and sulfate aerosols. We try to understand and improve the simulations of their emission, transport, chemical, and physical processes, and predicting their aerosol properties, life cycle, and distribution. And 2 things that are most important are the composition of the aerosols and their size distribution, because these properties can affect the aerosol radiative properties and how it interacts with the radiation. It also affects how the aerosols interact with clouds, changes the cloud albedo and scatter the solar radiation. It also affects how aerosols interact with precipitation. So that will affect the cloud lifetime and also the precipitation in general. And consistent with E3SM version 4 vision, we are trying to understand how aerosol and aerosol cloud interactions can be represented in coarse and fine resolution models, where we use fine resolution model to inform short-term scale features and use coarse resolution to inform long-term large-scale environment. And to achieve that, we really need the modern software infrastructure to enable this exascale computation to provide accurate and fast simulations at different resolutions to address the science challenges that E3SM is capable to answer. So the timeline of activities, so this is from our original planning back in 2019. We have these different efforts for aerosol cloud developments. And in year 1, we are going to do the development work. And then year 2, there's a lot of evaluation, refinement, and paper writing. And then in year 3, it's time to integrate these efforts into our general EAGLES master repo. And for the testbed, we have 3 activities: the large AT simulations, and the observations and regional refined mesh. And we have all these efforts going on in the last 2 years. Now it's also the time to wrap up those work and document and publish results. And it's also very important to know the integration plan within E3SM version 4. we have this E3SM V1 aerosol microphysics being refactored and partially ported to C++. And this co-integration starts to happen this year. And we're also starting to explore the chemistry solver options. And this is expected to complete in the following 12 to 18 months, and then integrate into the E3SM version 4. The improved treatments from EGOS as well as the current E3SM NGD M3 physics project will take the part that we are able to integrate into E3SM V4 in time and do that to meet our schedule. And that includes the aerosol treatments and ARI and ACI treatments. And there are also other interfaces like emissions, interactions with ice and mixed phase clouds and convective clouds, and other new developments that needs to happen between now and 2024, and then integrate before 2025. So of course, this is only a temporary plan, and we have we understand that E3SM version 4 has a very tight and well, just a very tight timeline. So we need to adjust as needed to ensure that we deliver a faster and better parameterization set that's fully connected within the E3SM version 4. And in the past 2.5 years, what we have accomplished is that we, just to summarize that, we addressed the structural deficiency by improving aerosols and ACI in the current E3SM. These new treatments include ultrafine and giant aerosols, wildfire aerosols, anthropogenic dust, secondary organic aerosols, and some aerosol-cloud interaction processes, including aerosol activation, rain characteristics and processes, turbulence, and how it affects the aerosol activation. And we also make significant progress on bringing aerosol and ACI parameterizations ready for convection-permitting scales. The second big accomplishment is that we're streamlining the machine learning to E3SM workflow, and we use cloud parcel model, MeCode, beam microphysics, and the newly developed LES model Pinnacles to provide a huge amount of data for aerosol cloud precipitation and meteorological data across different regimes. And we developed new physically regularized machine learning based parameterizations for aerosol and ACI processes and integrate those in E3SM assesses impact on the simulation quality. The third big accomplishment is to integrate observationally based process-oriented constraints for ACI in parameterization development. So in this effort, we developed automated aerosol and ACI diagnostics package based on ARM, satellite, and other observations to evaluate E3SM aerosol and ACI. The last but not the least big effort is to modernize the software for DOE's GPU-based computers. We redesigned the software infrastructure to improve efficiency, accuracy, and trustworthiness. And there's a solid progress on refactoring and transplanting the MAM aerosol microphysics code to C++ code codes. So I'm just going to go through a bunch of examples, and I know I have only 20 minutes left, so I will need to do a very quick overview, and I'm happy to direct you to the lead authors of those work, and so you can reach out to them afterwards for if you are interested in those efforts. So the first effort here is the nucleation mode aerosols that we found that it's important that we explicitly represent the ultrafine particles because they can further grow into Aiken accumulation mode aerosols and provide a increased background aerosol number concentration. That was the expectation, and Kai Zhang was the lead of this study, and he has reached the point of being able to identify that different nucleation mechanisms play different roles, but their effects are actually nonlinear. So if you, this is the present day droplet number concentration zonal mean plot, and you can see that if you turn off the boundary layer nucleation and do the difference, and this is the effect. And then if you turn off the binary nucleation and then do the difference between the two simulations so you can see the effect of that. But then if you add these two together, you don't get this result. This is by turning off both. So this shown that we are able to understand the mechanisms controlling the nucleation and their effects on droplet number concentration in E3SM. Next, I'm going to go quicker and quicker over time. And this is an effort to develop a better representation for wildfire aerosol injection height. And so in the past, the default treatment is the blue line, which is a prescribed injection height. And now we implemented the plume-rise model, which is the purple line here. And another one with the diurnal cycle is the red line here, but they are quite similar with each other. And this black line is the observation. So well, we show a significant improvement in agreement with the observation by implementing this new treatments to better represent the vertical distribution of the wildfire aerosols. And this work is led by Zhen Lu and Xiaohong Liu at Texas A&M. And this is an anthropogenic dust effort. And currently this source of aerosols is neglected in E3SM. But we believe that it has an impact on global aerosol burden, as well as its effect on radiation and aerosol-cloud interactions. So what Yang Shi and Xiaohong have done is to separate the leaf area index from the LAM model and then calculate the anthropogenic dust emission using that separated leaf area index. And then they found that well, it's a very important source in the US, northern China and Sahel region, and it actually accounts for about 25% of the global dust emissions. And to be ready for convection-permitting scales, we're also testing the sensitivity of the emission, the resolution of the emission data set that's being read in from by the model. So this is the original data set that's gridded to the 2-degree grid, and then in the SE dicor grid, and it looks like this. And then if we read in the original data set, that's a much higher resolution, and it looks like this. So you can see that we can start to show localized emission hotspots here, and that will affect significantly to the simulations when we go to higher resolution. So imagine if you run a high resolution E3SM in the future, and you're using this coarse resolution emission data, and then so your local aerosol concentrations and how it's being transported and interact with clouds and precipitation will be very different from if you're reading the high resolution emission data. And so those are the aerosol efforts, and I'm moving to the cloud and aerosol cloud interaction treatments now. So this is led by Vince Larson at the University of Wisconsin, Will Markey. What they have tried to do is to improve the PDF of the vertical velocity, subgrid vertical velocity, and then derive the correct updraft velocity within clouds and use that for aerosol activation or droplet nucleation. So you can see this is the current treatment. E3SM V1, V2 both uses the same treatment, that they use the square root of TKE, the grid box mean square root, grid box mean TKE, and take the square root of that and as an approximation for the updraft velocity, and use that for aerosol activation. And this looks like this, and we know that this is a very crude approximation because aerosol activation should only happen in the updrafts, but the grid box mean includes both updrafts and downdraft. So they have developed a new method to diagnose the updraft velocity in clouds, and this is the new treatment that looks like this. And Mikhail led an effort to use LES data to understand the autoconversion rate, and So what they have done is to use the compute the autoconversion rate from observed and LES model droplet size spectra. And because we have collected a huge amount of data and performed a large LES ensemble, so we have a large amount of data and compute this autoconversion across all different kinds of regimes. And they were able to use this to construct a new parameterization that includes the number concentration of rain drops and find a better agreement with the observations. So I'm moving to this large research component that we have in the ECOS project, which is to employ the AI ML to integrate data and models to improve aerosols and ACI in E3SM. So what we have done is to collect the measurements of aerosol clouds and precipitation and meteorology, and a lot of such data needs work to process them and to merge the size distribution data from different instruments. We also conducted a very large detailed process model and LES ensemble, and to provide a big training data. Right now we're at 50 terabytes and it's increasing every day. And we expect that in the current phase, by the end of this calendar year, we will reach 100 terabytes. And then we have more to do. And using this data, we can do this analysis and to understand and improve the design of parameterizations. We also use that to then develop the new machine learning emulators and then put that in the E3SM. So, and to put those emulators in E3SM, we use this Keras Fortune bridge, because the challenge is that the current E3SM v1, v2 is written in Fortran, while the machine learning tools are written in Python. So how do we integrate these two? And so this bridge is a very straightforward library, and Bauwinder was able to implement this in E3SM without too much effort. And right now it only needs the emulator as a text file, and it will just do the emulation, and this end-to-end workflow has been established. And certainly we understand that the next next version of the E3SM version 4 is going to be a hybrid Fortran C++, and the atmosphere component is going to be C++. So we have already investigated into the HPC aware methods involved that within the new software infrastructure. So just this study just tries to use the deep neural network to emulate aerosol activation. And what we can find here is that this is the original parameterization compared with the cloud parcel model truth. And from mode 1 aerosol ACAM mode and accumulation mode, you can see that the fitting is not really very good. So the updraft gain has some known biases. And this new deep neural network shows significant improvements. And when we put that into E3SM, we see an overall reduction of droplet number concentration in mean and high latitudes. And these are the known biases that I think the new aerosol activation parameterization is able to reduce. But we also observe these hotspots here, and we're trying to understand what's causing those increased droplet number concentration. We also did the PDPI aerosol emission pair simulations, and we found that with the new emulator, aerosol-induced radiative effects is reducing both short wave and long wave, and unfortunately that cancels out, so the net is still the same. And there's a question about how do you know that you are using the best or the most optimized emulators in the model. So this work is led by Sang-Duk Yu, and what he has done is to do this hyperparameter searching and try 40,000 different deep neural networks to search for the best configuration. So here is the mean square errors as a function of number of layers, and also he tries to understand the number of parameters as well. So he was able to identify the best the best deep neural network configuration with the affordable computational cost. Here is another example that we use deep neural network, and in this study led by Andrew Geis, he uses the random neural network to emulate the aerosol optics. And just the bottom line is that if you use the random neural network instead of the regular deep neural network, you can achieve the same performance with way less number of parameters. So that means the computational cost is way less. And compared with the original E3SM aerosol optics parameterization and this new neural network, we find that the accuracy is increased by 3 orders of magnitude. And this is the last example for the machine learning part that I want to introduce. And this is the auto conversion. And I think the challenge is that we have the limited predictability due to both limited data and understanding. So how do you determine what is rain and what is clouds? And so our approach is to collect all this data from field campaigns and do the LES to cover a wide range of conditions, and then try to understand and impose some physical considerations in the deep neural network training that includes the multi-scale physics, evolution of the DSD, and other environmental factors to better improve the auto-conversion process. So moving on to the software and computational part, I got 7 minutes left. I'm going to speed up. Here shows the process of aerosols and how it interacts with clouds. So unlike P3 and shock, MAM is invoked in several places by Em, and so it's not just down through one interface. So, and if you change the order and change how it's coupled, it's going to produce different results. And so we need to reorganize MAM aerosol microphysics and make it more, bring it to the modern software design. So this work is led by P. Bosler, Jeff Johnson, and others, and they have done this carefully to design how this should be rearranged, and then another effort on designing tests to make sure that the new software package produce the same or expected results as the original MAM code. So this is a new verification workflow developed by Bauwinder that they refactor the MAM in E3SM and then generate those input files and then verify this new code. And this is a new test tool to facilitate the comparison between the new MAM code in C++ and the old Fortran code, and then any intermediate version of the MAM code. And so basically you only need to provide a text file providing all the inputs variables, and then it will call the 2 different subroutines, and then create ensembles and then produce those nice plots so you can better compare the 2 codes and make sure the results are expected. So this work is led by Jeff Johnson and Qian Yang and others. And we also have dived into places where the aerosol processes can be bypassed, or so that we can speed up the simulation, but without losing the accuracy. And here, the work led by Jianfeng Li and Kai Zhang, they found that they can reach a significant reduction in aerosol optic property calculations if they remove the calculation of the properties for very small particles, and they have negligible impacts on the climate. And lastly is the efforts to develop diagnostics to better evaluate our model and for the routine evaluation and for identify new problems in the parameterizations. So this work is led by Shai-Qi Tan and Jerome Fast. What they have currently done is to collect the data from 6 field campaigns in the 4 geographic regions, And version 1 of the diagnostic package is released to focus on aerosol evaluation. And then version 2 is now being developed that includes long-term arm, etc. measurements for Aerosol-Cloud interactions. And so this is an example of Aerosol-Cloud interaction diagnostics led by Adam Warble. And this is showing the CDNC and CCN joint histogram. And, oh no, this is HEMAP. So you can see that the E3SM shows this slope, a very tightly coupled between CCN and droplet number concentration, while the observation shows not as steep slope. So that it means E3SM's cloud droplet number concentration susceptibility is much higher than the observed value. So the detailed analysis points to the problem of the aerosol activation scheme. So in our new aerosol activation scheme, we expect that this bias can be reduced. So there are much more great work to show, but I know I'm running out of time in this webinar, and just list a few of them here. So a lot of great work by this great scientists in the team. So summary, we are committed to deliver a better and faster aerosol and ACI parameterization fully connected within EMXX. We have made significant progress in developing improved treatments, and also for the new diagnostics and evaluation toolkit. We have made significant progress on refactoring and converting the MAM aerosol microphysics code to work with EMXX. The next steps include developing additional improved treatments, develop interface routines to fully connect aerosols within E3SM v4, and robust scientific evaluation to increase confidence and fidelity, integrate the improved treatments into EMXX. So thank you very much.